Hello and welcome back to Calculus 3. Guys, it's review time, which means it's exam time. I know, right? We have 3 people very excited about that. Yeah, and everyone else is excited. Good. What's exam on? Exams on problems you provided, I guess. And we have all of the sections. So chapter 12, sections 1 through 9. So we are talking about planes, more particular tangent planes. What else is very important? Gradients, 2D, 3D. Directional derivative. Surfaces / shapes. What else is important? Oh yes, I forgot. Partial derivatives. That might be important. And then chain rule. Now remember, chain rule is supposed to be the tree and calculations, right? So we have the chain rule. What else? We have, yeah, optimization. So min max. Min max saddle, right? That's the camel part. And we have Lagrange. And level curves. I think that linear approximation is under the tangent plane. So I'll just go like this and say was that your problems by any chance? So you felt left out? No? Linear approximation?
Oh no, sorry.
Lagrange? Yeah. No one's going to like you. All right, so we're looking at the standard kind of, 10 questions, quick calculations. Hopefully the problems you provide are not too long. I'll check especially the min, max, and Lagrange stuff. Again, depending on the spice level, we might have the replacement question, which is the 11th question in that case. If this stuff gets too crazy in terms of the length, I will have to maybe cut down to 8 problems. I don't know. Some kind of standard formula is the time it takes me to do it times 5. So if I'm not able to do the entire thing in about 15-16 minutes, it's a problem. So we'll have to then I'll have to adjust. So we'll try to have those, 10 questions standard, 10 points each one. But then if it's not possible, then I'll probably do 8 for, 12, 13 points each and see how that goes. What else? Standard stuff, no graphing calculators. No notes, formulas that you must memorize, obviously. Gradient is the vector of partial derivatives, equation for the plane, equation for the for D, right, min max, equation for Lagrange, right, del F equals lambda del G, equation for so chain rule is a procedure, it's not a formula. You have to create the formula using the tree, and then you take all the derivatives and work it out. Yeah, tangent plane, which is the plane, right? Instead of writing ABC, you're using partial derivatives, f prime, right? Fx, Fy. So it's the same thing. Just a question: what is the ABC normal vector? So, and linearization again is the tangent plane. So there you go. Is there anything else? So that would be it, right? Let's take a look at some problems then, since you guys. What was your problem? What is that?
That has all the chapters and the problem numbers.
Problem numbers from where?
From the chapters. From like the end. Exercise, that's everyone's question.
That are given to me?
Yeah, right now, if you want to use them. You're welcome.
See. Yeah, we just solve all of this now. Thank you.
You can take a picture one sec. I need a hard copy.
Mike, what is the? Well, 31.
Minimum distance to a surface.
Ooh, awesome. So, problem 31. Oh yeah, the yesterday's quiz. I don't know what happened, but I extended it throughout today. Today's quiz is open at normal times. Tomorrow should hopefully open on time. So you have 2 more. After tonight, you have 2 more quizzes to go. That's excitement. Minimum distance to a surface. Find the point on a surface 4x plus y minus 1 equals to 0. Closest to the point 1, 2, negative 3. All right, so this is the visualization for it. I'm going to have some kind of surface. I don't care what kind of surface it is. I have a point somewhere. So what's the closest distance? So this distance is to be minimum, right? From the point 1, 2, negative 3 to this mysterious x, y, and z. So what should I clearly have a constraint function here. That's my g. So I have g of xy given as 4x plus y minus 1 equals 0. Now, how do I find f? What should I use for f, which is the objective function? Distance formula, very good. So distance formula would be the one, because we want distance to be minimum. Therefore, distance formula is the square root. And now what do I have for distance formula? I have x minus 1 squared plus y minus 2 squared plus z plus 3 squared. That's the distance formula. And I have that now as the f. So f of x, y, z is equal to the square root of x minus 1 squared plus y minus 2 squared plus z plus 3 squared. And now for this one over here, right, we have that z is z0. But we'll deal with that later. So let's go. Del f equals to lambda del g. These are vectors. That's Lagrange. Now I need my partial derivatives. So what's fx? Well, it's going to be 2x minus 1 divided by the entire square root times 2, right? And then they cancel. Fy is going to be 2y minus 2 over 2 times square root. These guys cancel. And fz is z plus 3 times 2 times 2 times the square root. And then these cancel. Gx is equal to 4. Gy is 1. And gz is 0. So now, when we equal these guys, I have that x minus 1 over the square root is equal to 4 lambda. Y minus 2 over the square root is equal to just lambda. And z plus 3 over the square root is equal to 0. From where z is equal to negative 3 right off the bat. Now we equal these two equations, right, for lambda. The square roots will cancel immediately, and I will have that x minus 1 is equal to 4 times y minus 2. Right? They're both divided by the square root, and then when you multiply both sides, those square roots disappear. So, maybe I write those square roots there and then just kill them. There you go. So what I did is I replaced lambda into lambda, which takes this equation, right, and plugs it in there. And then the denominators cancel. So it's quick for us to see the relationship here that, so now from here, I have that x minus 1 is equal to 4y minus 8. So x is equal to 4y minus 7. Right? And I also have the g equation. Let's not forget that, which is 4x plus y equals 1. So that's the g equation. I guess it's set up for substitution, so just plug in. And I have 4 times 4y minus 7 plus y is equal to 1. So 16y minus 28 plus y is equal to 1. Plus y, so that's 17y is equal to, this is negative 28, so goes to 29 on the other side. Y equals 29 over 17, and we plug that back into x, right? So push that all the way up top to get that x is equal to 4 times y, so 4 times 29 over 17 minus 7. And we already have z, negative 3, up there. So all we need to do is to compute this real quick. What's this x? So 29 times 4, that's like a 30. So 126 over 17 minus 7 times 17, 41, 19 over 7. And then when you subtract, you get 1. What? Sounds good to me. So the point is 1, 29 over 17, negative 3. 116? How? Oh, yes. It's 120 minus 4. So 116, so that's negative 3 over 17. So the point is negative 3 over 17, 29 over 17, and negative 3, x, y, and z. And that's the point on the surface closest to the point that was given. Distance formula. Happy? Yeah. That's important. Talk to people to be happy. Let's see how many of you are smiling. 1, 2, 3, 4, 5, 6. That's a good amount. 7, 8. It's really funny, right? Lies. You're laughing. It's even better. It's joy. Yes.
For the, when you're trying to look for the max and the min after getting your C, like which place is the
F.
you plug it into that.
F is the one that you will find the partial derivatives for and calculate D and then go for the whole.
And that's
That's the objective equation. So, guys, we said that the Lagrange is giving you only the points where the stuff happens, but it doesn't tell you whether it's min or max. Now over here we only got 1 point, so yay, right? We're done. But if we were getting 3 points, let's say, and one of those points was supposed to be a min and 2 was supposed to be max, you want to know which one is which. So you would have to find fxx, fyy, fxy, compute the d, and then look at all of the, right? So Lagrange is giving you all these points, but it doesn't tell you whether it's min or a max. You have to still crank 12.8 procedure. However, in this case, we got only 1 point. Because we have 1 point, that means we're done. That's the min point, that's the min distance. You can find the distance by plugging. If this was an engineering question, they will not ask for the point, they will ask for the distance actually, because in engineering you want to know what the distance is. Maybe you are, putting a chain or something in between the 2 locations, or a cable stretching something. So you want to know the location, so you will be actually taking these numbers, plugging them back in the distance formula with the original point to find the actual distance between the 2 things. It's all about how you can make money out of this stuff when you actually start working.
So if I go to the job,
Exactly.
you didn't finish.
Did we talk about this in class?
Okay, yeah, we did. We shouldn't go there again.
Exactly. Because it's going to kill the review time. So,
Yeah.
yeah.
I'll promise no that.
Anything else? Yes.
For directional derivatives,
Yes.
finding the gradient and then dividing that by the magnitude, or
It's times the unit vectors for direction.
multiply by the
Gradient times the unit vector for the direction. Dot product.
which is the unit vector of the vector in the direction we're going.
Yes, in the direction that, yes. So gradient f times the u hat as a dot product. Which is the formula that you need to memorize for the directional derivatives for the I call it a argument. How many of you will there we go. Yeah, awesome.
Can we do another one? Can we do 12.2 number 69?
Well,
I don't know anything about level curve though. Or like 68 or 77 or
ooh. So which one is it, 68 or 69?
I guess 68.
All right. So we have 12.2, problem 68. It says, find an equation for the family of surfaces corresponding to f. Describe the level surfaces. And we have f, x, y, z given as x squared minus y squared minus z.
Can you say the question one more time?
Find an equation for the family of level surfaces corresponding to the function. This is page 884. So now, what are these level? What are you talking about? Level surface? What is that? Don't worry about it. The test is in 2 days. Nothing to worry about. Get home tonight. Make sure you chill. And then? And then game over. Okay. So let's say that we have, the shape that we saw earlier. So this lives on some kind of plane, and it's circular. And then you start cutting it. Yes. So each one of these, anytime you cut, you're cutting only with horizontal planes. And as you cut, you look at what kind of cut you're getting. So in this case here, for this particular picture, which may or may not be, representing our function up there, we get, in this case, circles. All right, so let's see what we get as we plug in over here. So what would I get for z equals 0? For z equals 0, I get f, which is x squared minus y squared. Yes. So what is it? It's a minus. Hyperbola. Now, z equals to 1, we get x squared minus y squared minus 1. What is it? Hyperbola again. This minus 1 is not going to change that. So this is the equation for hyperbola. No matter which z you pick, and you are only allowed to pick numbers there, because anytime you have z equals 0, guys, that's the floor in this room. Z equals 0 is the floor. Z equals 10 is the ceiling. Now, what's the height of this desk? Is like 4 feet. Z equals 4, each one of these desks. Not 4? 3? Fine. Z equals who cares? Awesome. That's the best one so far. So z equals who cares? It's going to be a number there, and that's a horizontal surface that cuts through. Cool? So now you see hyperbola here. If it was plus, it would be circles. If it was, right, something else, you can get anything in terms of parabolas or, whatever you can write as an equation. Better, Mike?
Wait, so then, yeah, what's the equation?
You can put it like this to encounter for all of the 1, 2, 3, 4, and so on. Yes. Anything else that you might be interested in? I did not put limits and continuity. Blasphemy. Okay, here we go. Wow. I'm also going to put domain in parentheses, right? Domain of the function. Because now it's xy plane. It's a region.
And with the limit, does that mean you're like replacing y with x and like trying out different things?
Well, it's not just with x. It could be x squared, could be sine x, could be any other. Yes. Anything else? Oh, look at that. Time flies when you're having fun. 3 minutes left, and then another 15 after that. Never. Hmm? Impressive. Yeah, why not? You did all the work. Any other questions? Anyone?
Yeah, 33. Can we do 33 or something like that?
I don't know.
Please.
33. Z equals square root of x squared plus 4y squared on negative 8 to 8 by negative 8 to 8. Those of you confused with this notation, it's giving us a region. Your calculators are negative 10 by the default viewing window on graphs is negative 10 by 10, and then negative 10 comma 10 by negative 10 comma 10. So this is what gives you x min, x max, and then y min, y max, like when you're setting the viewing window on your calculator. So the question is, graph several level curves for following functions. How do we do this? Well, obviously z equals 0. For z equals 0, we have the square root of x squared plus 4y squared equal to 0, from where x squared plus 4y squared is equal to 0, from where x squared is equal to negative 4y squared, and we see the no level curves because it's complex. From here you can get x over y, everything squared, equals to negative 4, and that doesn't work, so nope. Z equals to 1. So x squared plus 4y squared is equal to 1. And this is an ellipse. I hope you see this is ellipse, because you can write it as x squared over 1 squared plus y squared over 1/4 squared equals to 1. So this level curve here is going to be wide on x and narrow on y. You get 1 unit in x direction and 1/4 unit in y direction to graph this ellipse. Then you go z equals to 2, and you do the same thing. Oh yeah, 1/2, you're right. 1/2. So z equals to 2. We have square root is equal to 2, which is x squared plus 4y squared is equal to 2. Now, we must have equal to 1 for ellipse and hyperbola. Well, we have equal to 2, so you have to divide everywhere by 2. And when you divide everywhere by 2, you will get x squared over 2 plus 2y squared, well, over 1/2 is equal to 1. And now you can get those squares. So x squared over root 2 squared plus y squared over 2 over root 2 squared equals to 1. Again, the one on the left is larger, so it's going to be again level curve that looks like this, except now this is root 2 and this is, let's say, negative 2 over I want to say root 2 over 2. I don't know why I wrote this. There we go. 3, 4, 5, right? How many level curves on the test? 3, 4. Don't go calculating this for 18 iterations.
And then at z equals 16.
Already 45 minutes into the test, question number 2. So 3 or 4 of these should be sufficient. Terrible. Any other questions? I'm sorry. 12.3. Let's.
How about there are 3 sections that nobody that only got 2 problems submitted.
I
Forward, can you give an example of a question you might give us?
no, one is covered of those.
So 2. Can you give us an example of one that you might be giving us?
You will get it on exam. There was the.
You don't want me to type it up for you?
There was the deal. What do you have from 12.3?
I have it right in front of you.
I was talking to Mike. I know, it's beautiful paper. None of that.
On the left-hand screen again, or the
Which one?
19.
19.
I thought that was very easy.
Okay. Well, I don't know. We'll see. So this is now 12.3. Problem number 19. Limits at the boundary point. Ooh. So if it's limit on the boundary point, that means we are using some kind of algebra witchcraft to solve the problem. Nope. That's when you're showing that, proving that the limit does not exist. So this is one of those epic kind of problems where you factor something, and you can see that in the numerator you can factor out x, and then everything cancels, and the limit is 6, and you're done. It's a boundary problem. Yep. No.
It's not on there.
Yeah.
Okay.
So no. Nice. What about like 30? Ooh. Nice.
That's when you do that.
Yes. So limit xy goes to 0, 0. And we have x cubed minus y squared divided by x cubed plus y squared. All right, so we are trying to use multiple approach, right? So two-way approach or multiple way approach, to show that for different approaches, we get different value for the limit, which makes the limit does not exist. Technically, you are talking about a cliff. If you approach from this side, the limit is whatever this height is, say 3 feet. And if you approach from that side, the limit is 0 because it's on the floor for the same location in space, which is, let's say, the point in the corner. So we are going to look for different approaches, and the fastest, the easiest one to check is y equal mx. So when you grind through algebra, you will, first of all, this reduces the problem to calculus 1 limit problem. You replace every y with mx, and you won't have x going to 0 in that case because it's the only variable. And what happens is, if your solution is dependent on m, then you're done because it depends on which function you pick, right? Each m will have a line differently slanted, which is a different approach. If the answer, when you simplify this, is independent of m, that means that it doesn't depend on m, which means that you have to try different function. So you will get some kind of value. Let's see. So the pen didn't die today at all. What's going on?
It overheard you talking about it.
Oh. Do what?
Or you didn't have like a grand.
Oh yeah, I did not have any points to make. That's true. It only dies if I get excited and I want to do something. That's the time when it dies. So it reduces down to x goes to 0 for x cubed minus mx everything squared divided by x cubed again plus mx squared. Don't forget to write this limit every time because it's minus 1. So now you can factor out x squared on top and stay with x minus m squared. And you factor out x squared in the bottom, and you're left with x plus m squared. Now these guys cancel. And if you do 0, right, you get negative 1. Answer. So the limit is negative 1 no matter which linear line that goes through the origin you pick. Now you can't go away from the origin because you see that xy goes to 0, 0, right? 0, 0 is the origin, so you better pick that point. So now what you're seeing here is that if you pick infinitely many approaches, they all go to minus 1. Now, does that mean that the limit is minus 1? Hell no, because we did not approach it as a sine x, as a cosine x, we can't approach it as a cosine x, because that will keep 0. We shift cosine, right? You can approach it as a tangent, you can approach it as anything that goes to 0. So what I'm going to do now is the family of quadratics. So the next one, because this one didn't work out, I'm going to try y equal mx squared. Plug that in, see. So I'm kind of going to change these functions and play with it until I get an answer that depends on m. Or I get an answer that is different than negative 1. So now I have that as a condition as well. So every next calculation must have the same negative 1 for no matter what I try, if that's the limit. Okay, so I have x cubed minus m squared x to the 4th divided by x cubed plus m squared x to the 4th when you plug in. Limit x goes to 0. Factor out x cubed on top and the bottom. We are left with 1 minus m squared x divided by x cubed 1 plus m squared x. And then these guys cancel. And look what I get now as I substitute 0. 1. Not the same. Limit does not exist. Boom. Maybe I should say at 0, 0, right? Because it exists somewhere else. So you're looking for a value that it's either different than the one you established before, or you're looking for the answer that it's going to be in terms of m.
Do you have to say why, or is the proof in the math? Like in Calc 2, I had to say for Thornberg's class, like limit does not exist because -1 does not equal 1.
That's a theorem.
Yeah.
So you are technically stating the theorem, which is what I did with the arrow
Okay.
when I wrote not the same. So yeah, that's the two-approach theorem. So sure, why not? So
But also
yes.
an arrow saying not the same word.
You forgot what you're going to ask?
Yeah.
The arrow will suffice. Make it a nice arrow. See? There we go.
Are absolute limits like rare in 3D?
What do you mean absolute limits?
I'm not absolute limits. What like do they exist a lot? It doesn't seem like we get a lot of finite limits.
No, the problems that you are looking at are rigged because it is extremely difficult to compute limits if it's not just plug and chug. We have it kind of easy if it's a boundary point, if you can factor, right? Massage it with algebra. We have it kind of easy for these to show does not exist. But to show the boundary limit that, you know, which exists, tough job. All right? So it's a little bit rigged, all right, in terms of the questions. But you have to understand the limit is just a y value that is computed. So you draw the same parallel like you did in a Calculus 1 class when you say, pre-calculus class, when you say f of x is equal to x squared, f of 3 is 3 squared, which is 9. Same thing with the limit x squared as x goes to 3 is 9. They compute the same value because it is at the end the same value, but they compute it in a different way. Right? This one, the first one computes it directly as 3 times 3 is 9. The second one computes all of the points around number 9 without computing at 9, and then it screams, hey, it's 9. Right? That's the limit. Far more powerful method for computing. Even though for practical purposes, we plug in 3. Right? But we know that we are able to find the limit if there is open circle and a function and a point is missing, where the other one, right, the pre-calculus would just tell us does not exist. But calculus gives us more information because it will say if it existed, it would be 5/2 or something like that. Any other questions, concerns about life or otherwise? We have negative 3 minutes left. See you, Joe. All right. I will see you all at some point on Wednesday.